Okay, so I'm gonna do a quick debug loop of the main training loop. There's a couple concepts that I want to touch on that I think are unique to this project. One being the model structure, one being kind of the generator format, and then the other being the loss function that's actually used in this project. But I'll just explain to those as we get to them. So this is the training function here, train batch. Here's the parameters being passed in. So we have our batch size, we have epochs, learning rate, a couple other booleans. Some of them, so shutdown determines whether my PC shuts down after the loop is finished. These models can take quite a while to train, so that was useful at times. And then we have like a bunch of boolean flags. So if we're loading an existing model, if the model has phonemes as its target or letters, and I'll explain a couple of those labels as we get to them. So stepping in, we have our device being set to either the CUDA device or the CPU. We're using a letter model here. And so I can, here's my code containing all the models. I should mention that this project is based off, so the Wave 2 Letter project performed by Facebook, or Facebook's AI sort of wing. The model is pretty straightforward itself. I tried to follow this paper about as closely as I could. Here's kind of the model structure. It's fairly simple. It's just a lot of one-dimensional convolutions stacked on top of each other with these channels and these kernel widths. The paper contained a lot more useful information as well, just on how they formatted their data. You know, like stuff such as sampling rates, and I mean there was a lot of useful information contained in here, but here's where I got the model from, so that's what I'm following here. So for the wave to letter model, basically we have our input, the channels that we have. So we have the base channels times 3 because we also have the first and second derivative. And then our output is 250 channels, and basically we're just following that model structure. It's pretty straightforward. So we create all these convolutional layers, and then one of the key things is we have an output of 29. So the reason that is 29, I guess it's also worth touching on this now, is to do with our loss function. So we have 28 target characters here. And 0 is occupied by this sort of special blank character. We'll talk a bit more about that when the loss comes out, but the point that I want to make here is you kind of have your n plus 1. So however many target characters you have, you need one extra one on your model. And then the forward function is simply just passing the output of one function to another, and then we have log softmax at the end. So going back here, we now have our model set. A whole bunch of stuff that isn't really important for this video, but about just kind of where these where the outputs are saved and that sort of thing. I think that we're okay. So now we're setting the loss function. The loss function is a little bit is pretty I suppose unusual and complex as loss functions go. It's called CTC loss, connectionist to temporal classification. Basically, this is a loss function that lets us, this isn't a standard kind of machine learning machine learning application, in that we have our inputs are of unknown length, so the audio file can be of a varied length, and our output is also of a varied length. The sentence can be long or short. So CTC loss is a loss function that lets you map two sequences to each other of unknown lengths. And we'll talk about the output later on, but that was one of the kind of major, key points of the project, was getting that to work. Optimizer, none of this stuff is really important for the video. We're not loading a model. Yeah, we're gonna... And now we can enter our training loop. So we have our training and our eval stage. and now we create our generator. So our generator is first off, we're passing a lot of the important flags that we were earlier, so the normalization and 2D flag, and also we're calling a different generator if it's a phoneme model or not. So we'll step into that in a sec. Here we have our generator. So data generator torch batch. This is a letter generator. So the 2D flag, I can talk about that now. So basically here we're just accessing the data that we processed earlier. So that data is held, for example. Let's just look quickly. Process data, and we have our train. We'll be looking, I think, in here. So this would contain a, I don't think that this will be legible or anything, yeah. But, and then we have our phonemes in here. So that's where our data is held, that's where we're navigating. So we shuffle these files, we have our target map here. So our target map here is the letters. And then we have this getX. So this is how our, so the X being sort of the input data, or how the audio files are being treated. So the is2D flag, basically this is like this is a variation that I tried that I thought might be useful. So in here we have, this is the non-2D flag, and you just have your 13 channels, and, excuse me, so you have the 13 channels times 3, right, and so you just have them kind of like stacked parallel to one another. What I was doing in the 2D ones is down here, so you would just have 13 channels, but they've been concatenated on one layer. So like basically we're taking so say looking at them at the channels slice by slice. On the 13th channel, then below it you would have the differential of the 13th channel, and then below that you would have the differential of, you would have the second differential, but those would all be on one channel that is of height 3 and then of the original length. So that's what the 2D flag meant. The normalization just means we're normalizing it, so to get the mean of 0 and the standard deviation of 1. So that's what's happening here if we step into getX. So we have is2D is false and normalization is true, and we're just returning a we're returning this getX. So normalize, concatenate. So for the ones where it is 2D, we're concatenating on the first axis to get that vertical stacking that I mentioned, but on this one we're just concatenating them normally. So we return, and then this, we're just opening a file. We get our sentence. So our sentence here is the target like outputs, so not letters, but instead the integers that represent the letters. So each one of these, we should have spaces. So the 28, I think, is the space character, or is it 27? No, I think it's 28, because 28 seems to be appearing more. And then each of these is words. Or like the in between each space character are the letters. So we're appending that to our X, depending on our batch length here, how many we return, or excuse me, that is our target data. So that's being appended to this Y list. Our X data, we made our getX function, and our XY here is just kind of simply the 13 coefficients output, and the two derivatives, and then the sentence itself. So that's what's happening here. We can step out now. This is, yeah. So this should have a step out and go back to the Wave2 ladder. Okay, so now we are outside of the generator function again. We have our, we can take a look at our X, which I believe is a list. But if we were to take a look at that, so we have our 39 channels, and then this one's of length 314, and then for our Y, we'll have those sort of, well, they're padded, but sequences of target integers. So yeah, this happens with PyTorch. Does not does not gel well with debuggers. This has happened in this is the second project where I've had to deal with this, but basically the debugger is no longer, like this variable explorer is no longer responsive, and also the UI freezes, so we just kind of have to do it blindly now. The rest of this is not particularly like complicated, or basically, you know, it's just a lot of like finicky stuff about squeezing, unsqueezing, and you know, making sure the predictions are in the right format, that sort of thing. But we have our predictions being generated here from our model. We need our prediction lengths. The loss function here basically needs to know, because our predictions are, we're passing them in a NumPy array, but the sequences will be of different lengths, so we pass another array that gives the lengths of each sequence, so it knows how many to ignore, and we do something similar for the input as well, because the inputs are also of varying lengths. So that's basically what's happening in this loop. This is just iterating through the data that we got from our generator, and we're also making our target kind of final array here. This is the format that's required for the loss function, so it naturally comes out in this sort of format, channels, then the time dimension. But here we're transposing it into time, and then the channel dimension, and then it actually goes time dimension, batch dimension, channel dimension for the actual loss function. And then here we're just calculating some useful, we have like a running loss that I'm sometimes outputting, and if it's in a training phase, we're training our model. And if it's not in a training phase, then we're kind of just like recording stats for the run, and we can update, yeah, we're updating like our best loss metrics, metrics like that, and if it's our best model, then we want to save those weights. And if it's not our best model, we can load the best model again. So if it's regressed, when you finally have a mature model, you might want it to take the best weights again, rather than try and recover from the detail that is lost. That's basically the training loop. So the output is treated with a decoder function. I actually want to talk about that in a different video. The output is of the format of, for each time step being input into the model, it outputs a probability, you know, kind of like a normalized probability array for each of the target, for each of the possible targets. And we'll be talking about how to treat that and how to like decode that in the next video.